The heap is a completely kind of different animal, so the heap is where the garbage collection rules. So now we're going to talk a lot about garbage collection. And it's again, it's a beautiful abstraction because you can just throw objects at it and somehow magically they disappear at some point and you don't have to worry about it, except you kind of do. And what we're going to talk about is actually kind of why you do have to worry about it and what are the possibilities right now to kind of what garbage collectors there exist right now in the heap, and also like what the future interesting developments that happen. So, hello. There you go. So I'm actually going to show you so we're going to talk a lot about the mark sweep or mark compact algorithm, which basically works by marking all the live objects in the heap. So it starts with the root set, which is basically your static fields, your local variables in the running threads. These are the things that are holding everything else in memory. And the first phase of this marking phase is basically the usual breadth first search algorithm on the graph. So we start with the set, and we start following all the references, and just like and try to visit every single node in the graph that can be visited from the root set. So once we did that, if you look at here, then in the end the visited set is the live objects, and everything else is garbage. So this basically this little piece of code returns in the end all the live objects on the heap, which is pretty neat and small. The cool part about we have a queue where we add things that we will be looking at, and then we follow references and add things that we visited to the live objects. So the neat thing about it is that it's if you look at it, it's pretty parallelizable. So if we just have a if we have a synchronized queue structure, and then we just take things from it, and we have a synchronized visited structure, then we can just throw multiple threads at it and just kind of crawl the heap in multiple threads. It shouldn't be too hard. Yeah, it's a pretty straightforward. We have just several while loops cranking at the queue, cranking at the visited. It's maybe we visit some places a couple of times, but we're not going to visit the garbage anyhow. So. And this is going to be very useful. So the mark compact works in three phases. The first one is mark, and once we mark things, then we have objects marked as live. And here's like here's the root set, here's the heap, here's the objects marked as live, and everything else is garbage. Now the second part of it is the relocate phase, where we ignore all the garbage, and it can be in the same heap region, it can be in a different heap region, but we take objects one at a time and we copy them in the beginning of the heap, like one after another. Why is it done? Well, so that the allocation will be really, really cheap. So when you allocate a new object, if you have everything like going one after another in the heap, all you have to do is increment one pointer, and say that this is now the object, this region in memory. So you can, it's really cheap operations, a few clock cycles to allocate. And in Java is a lot of things are optimized to allocate as quickly as possible. So this is one very useful optimization. But after we relocated the object, we have one more step to do, and this is the third step. It's called remap, and this is when we go through all the objects and update the references from the old locations to the new ones. So objects actually have direct pointers to each other, because otherwise it would be extremely inefficient. And we have to update actually numbers, these indexes into memory. We have to update them to the place where objects now are. So we have three phases, and there are a few problems with those three phases. The main problem would be that, the mark compacts, because we basically doing something on the heap, on most of the objects of the heap, then the running time is proportional, like the O is of the size of the heap. And another thing is that because of relocate and remap, this operation, they basically update the heap, then we cannot continue, we cannot have the program running during that time. So we have to stop it. And this comes the famous stop the world problem. And the biggest issue nowadays with the garbage collection is that the stop the world time is proportional to the size of the heap. So which means that if you increase your heap 10 times since a few years ago, then which is quite common memory but much cheaper, then what you have is that you have stop the world now measured in minutes, which is which is things that you totally see in the terabyte heaps and even in some gigabyte heaps, depending on their complexity. And this is kind of a horrible issue because one thing you don't want to have is that your user suddenly, yes? Sorry? Yes, that's a very correct observation, but usually the size of live data is proportional more or less to the size of the heap. So you don't usually have 90% of garbage. If you have 90% of garbage, something is horribly wrong with the application. So, but it's a very correct remark. Yeah, so this is the problem. This is what we're going to discuss. We're going to discuss what what concurrent algorithm exists to kind of help solve this problem. And they actually already, mostly are in the JVM, so we can try them out. As a side note, this marking phase means that your garbage collection algorithm will always visit all of your heap regularly, pretty damn regularly, which means that if you have any part of your heap in a swap file, then every single page in that swap file is going to be swapped in and then it's going to be swapped out. And this is going to destroy your application. This is going to grind it to a complete halt. You're going to be using 95% of your time, if not more, swapping in and swapping out. So as always, I recommend that you turn off the swap file in production, because if your application runs out of physical memory, it's rather better than it would just die, just throw an exception and die, than it would actually start swapping, and then you don't know what's happening, but nothing works. So this is something I always recommend. Okay, so let's look what garbage collectors are there. So one of them, I think it's even default in the JVM right now, though I'm not 100% sure because they change the defaults all the freaking time. One of them is a parallel mark compact, which has a very easy idea that let's just use original as a serial mark compact, which just use one thread for stop the world. Now let's use as many threads as we can, as many threads as we have cores to do the garbage collection. And it's all very nice. Unfortunately, it's not there isn't like win X times, because it's not fully parallelizable this way. So unfortunately, even though it helps a lot, but it doesn't really fully solve the problem. But it's the first kind of useful thing. So another thing that there is the concurrent mark sweep. So this is not mark compact, this is mark sweep, which actually does the marking parallelly in one thread, and then does this concurrent sweep. So it has a very, very short stop the world phase. It's actually, if you want to optimize for short garbage collection poses, then probably the concurrent mark sweep is the best. It is called the CMS actually in the settings. Then it's probably one of the best options right now. The only issue with it that it optimizes the garbage collection cost, but it trades off on the allocation cost. Because remember, like the compacting, this copying everything in the beginning of the memory, this is what it doesn't do. So it only does the marking, and then like it holds a list of free, of garbage objects, which are now basically free, and when you allocate an object, then it puts it in one of those slots. And if it runs out of slots, then it still has to do the compacting phase. And actually, so there's two problems with it. One of the problems is that allocation is more expensive because it's not just increment the pointer and that's the allocated region. It's now we have to go through